In order to determine if the process is in or out of control, we first have to measure it. We can break the process of measuring the process down into 5 steps. The first step is to take samples from the process, measure each, and then calculate a sample statistic. For example, suppose we want to measure how a cereal box filling line is performing. We often want to sample at regular intervals, say every hour. So in 1 hour, we may randomly select a sample of 5 cereal boxes. We weigh each one and then take the average of those 5 boxes. This is our sample statistic. In the picture, each green box represents that sample statistic for the hour. After enough samples are taken, a pattern emerges. If the process is stable, we should get a predictable distribution. Here, the solid line represents the distribution of the average sample weights for the cereal boxes. It appears to follow a bell-shaped distribution. As you will recall, there are many different types of distributions. The most well-known is the normal distribution, which has a bell shape to it. The normal distribution is actually a family of distributions. A particular normal distribution is described by its central tendency and dispersion. In other words, its mean and its standard deviation. Distributions can also take different shapes. The far right picture in this example shows a right-skewed distribution and reminds me of a beta distribution. Step 4 tells us that if only natural causes of variation are present in the process, then the output measurements form a distribution that is stable over time. This is a very good thing because it means that we can predict how our process will behave in the future. If, on the other hand, assignable causes are present, then the output is not stable over time. That means it is difficult, if not impossible, to predict the output of our process. Once we have measurements of the process, we want to create control charts. The purpose of a control chart is to help us distinguish between natural variations and variations that are due to assignable causes. In the case of the cereal box example, the horizontal, or the x-axis, would be time, in our case, each hour. The vertical axis would be the mean sample weight for 5 cereal boxes. The solid center line is our target value. That's probably going to be the weight that's printed on the box. The 2 dashed lines are the control chart limits. If the sample statistics fall within these limits, then the process is probably in control. We'll talk more about this later. The last sample appears to land on the upper limit control line. Just like in tennis, if it hits the line, it is still considered in. For the cereal box example, it is important to take a moment to consider why we care about being either below the lower limit or above the upper limit. If we are below the lower limit, we are cheating the customer. If a consumer watchdog group finds out that we are underfilling our boxes, we could be sued or taken to court or whatever. What about being above the upper limit? Basically, that means we are giving product away for free to the customer. This could cut in the profit margin, so we want to be aware if we are overfilling the boxes. In general, we can divide the possibilities of the results of process control into 3 categories. First is the process is in statistical process control, and we are capable of producing within the control chart limits. This is the best case scenario and the one we are hoping for. We'll come back to part B in a second. In the example illustrated in the part C, the process is out of control. That is, the mean and standard deviation continually fluctuate, making it difficult to predict the quality of our output. And then finally, going back to B, we have the case where we are in statistical control but are not capable of producing within the limits. See how much green on each side is outside the control chart limits in part B? By being in statistical control, the process is consistent in its output and we can make predictions about future outcomes. However, we see that the dispersion is too wide to be capable of producing to the standards that were set for the process. This may mean several things, one of which is that we need better technology to help us reach the capability we have for our product outputs.